Then I also just want to spend some time working on problems, letting you work on problems, and then I'll go through them. So first of all, does anyone have any homework questions you'd like me to do? Sure. You have it with you, the problem? Okay, number 2. There's a pin joint over here. And a roller in the middle. No, that's number 1. Oh, but they're both the same. Roller in the middle. And then there's a distributed load like this. With a maximum value of 6,000 newtons per meter. The total length is 3.5 meters, so this is 1.75. And this is. And there's also a weight, 500 kilograms. So the mass of the beam is 500 kilograms. And we want to calculate the internal loads. All right, so first of all, this is a case where we have 2 different distributed loads. So a free body diagram of the whole thing looks like this. I'll call this RA. And then over here we have a vector RB. And then we have a distributed load representing the weight. If the mass is 500 kilograms, the weight is 4,905 newtons. And the total length is 3.5. So the distributed load representing the weight is 4,905 divided by 3.5. What do you get for that? (1401.43 newtons per meter due to the weight. And then we also have that externally applied 6,000 newtons per meter from that triangular distributed load. And we have to deal with both of those. So the total weight force is 500 times 9.81, and then I divided that by the length. So if the length is 3.5 meters, then each of those 3.5 meters has, this much newtons if it's a uniform distributed load. And now that first we have to isolate the whole body. And once we've chosen the body to isolate, we can represent those distributed loads as point forces. So let's draw those out. So there's the triangular one. The whole length is 3.5. The height of that triangle is 6,000. And so the total force is 3.5 times 6,000 divided by 2. So that's what, 10,500? And then for the weight force, it's a rectangle with a height of 3.5. Well, we already know what that is. That's just the total weight. 3.5 times 1401.43 gives us back the original weight of 4,905. So the free body diagram looks like this. We have an upward force RA, a force vector RB. The weight acts at the center of the beam, so that's 4,905 right in the middle. And the triangular distributed load acts 2/3 of the way from the left to the right with a magnitude of 10,500. Newton's second law says 0, negative 4,905 plus 0, negative 10,500 plus 0 RA plus RBX RBY is equal to zeros. So there's no RBX. And then the y equation says RA plus RBY equal to negative 15,405 positive. Okay, so this one we can't solve yet, but we'll use that in a second. And then the moment equation, I'll use, I guess the midpoint is the about point. That'll get rid of 2 of those forces. So, no, I'm not doing that. That's crazy. I'm putting it over here. Okay, so first, the force of 4,905 has a moment arm of 1.75. And if the red dot is the about point, does this rotate clockwise or counterclockwise? Counter, that's positive. And then the RA has the same moment arm. It's directed the other way. So that's 1.75 RA. And then the 10,500, that distance is 1/3 of the way from the right end to the left end. So that's, this moment arm is 3.5 divided by 3. And which way does that go? That's counterclockwise, so plus. So what is that? 1.16 repeating times 10,500. And then there's no moment from the y component of RB, so this is 0. And so we get 1.75 RA is equal to, what do you get if you add up both of these 2 constant terms? Okay, so what do you get for RA? And then what do you get for RBY? Okay, and RBY. All right, now we know all the external loads. So now we have to figure out how many cuts we have to make. So let's go back up to this original free body diagram. So there's the 2 endpoints. And then we're looking for points where there are point loads applied or where functions for distributed loads change. So where do either of those things happen? Yeah. So the only place is at A in the middle. And if instead of going all the way back to your first free body diagram with the distributed loads, you went back to this one where we'd already represented those distributed loads as point forces, it would lead you astray because you would think that there was a point force acting at the middle and a point force acting where that 10,500 is acting. But that's just a mathematical thing. That's not a real load. So you don't want to do that. Okay, so we need two cuts. Cut 1 is valid for x's between 0 and 1.75. So first I'll draw everything on there. We have the downward force from the weight. I'll draw it under just to make it look a little neater. This is a distributed load of 1401 point, what was it? 43. The total length is x. And then we have the triangular distributed load. We'll deal with the height of that in a second. And then we have the internal loads, T, V, and M. Okay, well, to get the height of this distributed load, we're going to use the function for a line that says the slope, so, mx plus b. The slope is the total change in the height over the whole length of the beam, so that's 6,000 divided by the total run, the total length of the beam, which is 3.5, times x. At x equals 0 on the left end, that has no, the distributed load is 0, so there's no y-intercept. What's 6,000 divided by 3.5? 1714.29x. Okay, so normally, so I called this y just in the equation for the line. Usually I call that the function q of x, but there's something important to notice here. Q of x is the function representing the entire distributed load. And so there's going to be one function representing this one in this case, one representing this one. And the total distributed load function, that total Q of x, is this plus this. So Q of x is equal to 1714.29x plus 1401.43. And so when we do the derivative check and we take dv dx, this is what we're going to be comparing it to. Now that we've chosen the body to isolate, we can represent those distributed loads as point forces. For the rectangular distributed load, that's going to act right in the middle. And the total area, since the length is x, the total area is going to be 1401.43x. And then the triangular one has a length of x, a height of 1714.29x, divided by 2 because of the formula for area of a triangle. And so you get 857.14, something like that. 857.14 x squared. and then the internal loads. Anybody have any questions about calculating those point forces? What? The triangle that we're dealing with is like this, with a length of x and a height that I figured out here from the equation for the line, 1714.29x. And then the area is those two multiplied together divided by 2. And then the internal loads, T, V, and M. So Newton's second law says 0, negative 1401.43x plus 0, negative 857.14x squared plus t negative v is equal to zeros. So there's no internal tension. And then the shear force is negative 857.14x squared minus 1401.43x. And then the moment equation with the about point at the left end. The moment arm of this 1401 force is x over 2. It's right at the midpoint. So we have a clockwise moment with a moment arm of x over 2 and a force of 1401.43x. And then we have another clockwise rotation with a moment arm of 2x over 3 because of the centroid of a triangle, and a force of 857.14x squared, and then plus m minus vx is equal to 0. So m is equal to vx plus, what's 2/3 of 857.14? 571.43? 43 x cubed. And then plus 700.71. Yeah. I like to just celebrate my human autonomy by throwing away significant figures at random. Right, not rounding, all sorts of stuff like that. That's right. Yep. You got it. You know where I'm coming from. Okay, so let's see. So this is x squared. And so m is equal to, so we have negative 857.14 x cubed minus 1401.43 x squared. I guess, tell me what negative 857.14 plus 571.43 is. Those are both x cubed terms. So negative 285.71 x cubed, and then minus 700 point, let's call this one 72. You got a problem with that, Harold? Okay. I think this is right, isn't it? Because this term is squared, but we're multiplying it by x. Okay. All right, so this is the function for the bending moment. And these functions, these subfunctions are valid only on the interval x from 0 to 1.75. Yeah, so I already subtracted that, yeah. So, right, and you have to have these like partial cancellations like this to make the derivative things match, because you know, the derivative of this function here has to be equal to that, and the derivative of, so anyways, you're always going to have, whenever you have higher powers of x than 1, you're going to have these cancellations of terms. Right. Yeah. Okay, and then cut 2. This is for x's between 1.75 and 3.5. So now we have, we do have that force RA. We calculated that before. 11,905. So that's in here somewhere. And we have the internal loads. And then those two distributed loads, since those functions defining the distributed loads didn't change, they're going to appear, you know, nothing changed when we crossed over to this point with the triangular or the rectangular distributed load. So we're just going to include those the same way we did before. There's going to be a downward force from the weight of 1401.43 yes, that's right. 1401.43x. And then there's also going to be the one at 2/3 x, 857.14 x squared. And then Newton's second law says 0, negative 1401.43 x plus 0, negative 857.14 x squared plus t negative v is equal to zeros. Yep. Plus 0, positive 11,905. And so t is equal to 0. V is negative 857.14 x squared minus 1401.43 x plus 11,905. Yep. Actually, that would be a good idea, because right, because if you made a mistake calculating v, then you're going to have to redo everything at the end. And then the moment equation. We have the 1401.43x with a moment arm of x over 2. And that's a clockwise moment. And then minus 2x over 3 times 857.14x squared. And then what's the moment arm for the 11,905? Yep, that doesn't move. That doesn't depend on x. That's just always halfway, 1.75 meters from either end. So, and that's a counterclockwise moment. So plus 1.75 times 11,905. And plus m minus vx is equal to 0. And so you get m is equal to vx. And then these two terms are going to show up just exactly the same way they did in the last cut. So what were those? Positive 571.43x cubed. And positive 700.71x squared. And then we have this extra term. What's 1.75 times 11,905? $20,833.75. And now multiply the shear force by x and substitute that in. So we're going to have two partially canceling x cubed terms. What's minus 857.14 plus 571.43? Well, it's whatever it was before, I guess. So that's minus 285.71 x cubed. And then for the x squared terms, we have minus 700.71 x squared. And then we have plus 11,905x minus 20,833.75. And now you can do the derivative checks. Derivative of m is negative 857.14 if, 3 times 285. And then 2 times 700.71 is 1401.43. Derivative of this is the constant 11,905. So that works. And then the derivative of the shear force, this is negative 17,1714. Where's that? 1714.2, 8 or whatever. That was a round off. Times x minus 1401.43 compared to up here 1401.43. Those derivative checks work. And then let's think about where we expect, so at the endpoints, let's just think about where we expect non-zero values for internal loads. Okay. So let's look back at this original picture and think about what's happening at the 2 endpoints. At this endpoint, is there a horizontal point force? No. Vertical point force? No, that's a distributed load, so it's not a finite point force. And then there's no couple. And so we expect all of the internal loads to be 0 for x equals 0. And then at the other end, there's no horizontal point force, and there's no moment, no point couple. So we expect the tension and the bending moment to be 0 there, but there is a vertical point force coming from that pin joint. And so we expect there to be a non-zero value for the shear force. And if you look, then you can just plug those values back into the functions that are valid at those endpoints and compare. Question? If you mean don't do the rotational equation and just do the integral, is that? Mm-hmm. To just figure out where the endpoint is? Yep. And then, by the way, I didn't say that this is like one of my checks, but right here we have, I don't remember what that force is, but like 11,000, well, 11,905, right, was this vertical force. So whenever you have a point force in the middle somewhere, there's going to be a jump in your corresponding internal load that's equal to that. So if you look at the change in the shear force, there's a jump in the shear force right at this point with a magnitude of 11,905. Yes, you can do that. I think you'll find that it's not really, I mean, it's not really that much harder or anything, but it's not really any easier either, you know. But yeah, you can do it that way. Any other questions? Okay. So let me give you the sort of the final type of distributed load that you have to deal with. So let's say we have a beam that's connected to the wall on the right side. And you have a triangular distributed load like this. Let's say that the length is 2 meters and the height is 5,000 newtons per meter, and we want to calculate the internal loads. Sorry, I drew this backwards. That's the kind we've already done. So now the 0 is over here, and the 5,000 is on the other side. What are the internal loads? Okay, so we're going to see that. So we always do these problems working from the left to the right. And we're going to see that it's surprisingly complicated to do a problem like this where the triangular distributed load is facing the other way. In practice, if you had some research problem or something for a company and you had to get a rough calculation for this, I would recommend in this case you just walk to the other side of the beam, and then that triangular distributed load is facing the other way. But there are problems where you would have to do this. Like, for example, I think there might be one actually in the problems where there's one going one way and one going the other way. And then you just can't really get around it. So let's just talk about how to do this. Okay, there's a fixed joint on the right side of this beam, and the right side of the beam never shows up in the cuts. And so we can do this problem without calculating the external loads. So if you notice that, it's always a little bit of a time saver. Don't need the external loads on the right end. How many cuts do we need? Just one, yep. And so our cut 1 is for x's between 0 and 2. And I'm going to draw this cut out with a light colored thing representing the part of the beam that we're ignoring. And so we're doing the cut. So there's that part of the triangular distributed load and that part. And the thing that makes this a pain is that when that triangular distributed load is facing the other way, you just make it a different triangle. But look at what happens here. Like if you cut off the point, you take away the thing that makes it a triangle. So now we have this different shape that we have to deal with. We have to deal with this trapezoid. We do know the magnitude over here. This distributed load value is 5,000 newtons per meter. So that's a little easier than before. But over here, we have to, think this through kind of carefully. And then we have the internal loads. Okay, so the problem we have now is this is a trapezoid, not a triangle. All right, so the way we're going to treat this is we're going to treat it as a triangle sitting on top of a rectangle. We know that the total height over here is 5,000. But we don't know yet the height of that rectangle. Once we do figure this out, we can just treat it as two separate forces. We have one point force that's equal to the triangular distributed load acting a third of the way from the wall towards the point, and then 1 point force representing the rectangular distributed load acting at the middle. And what we need to do that is we need to figure out how tall that rectangle is. So how do you think we can figure out the height of that rectangle? The equation for that line. So y is equal to mx plus b. Over the whole length of that shape, what's the rise? Negative 5,000. That negative's important, right? That's a negative slope. So y is equal to negative 5,000. And then what's the run? 2, the length of the beam, times x. And this time there is a y-intercept. What's the y-intercept? 5,000. Yep, good. And so the equation for this line is negative 2,500x plus 5,000. And since the variable x, our cut, this cut represents an x value that's equal to where the right side is. So the variable x represents this location. And so this function tells us the height of that line at the point x. Okay, so that gives us the height of the rectangle. So the height of this rectangle is negative 2,500x plus 5,000. And one important thing about that is, at first glance, you might think that that is a negative value. But if you plug in the values of x ranging from 0 to 2, this is actually positive. So remember, this looks negative, but it really is a magnitude. It really is positive. And then I guess the other thing that we need to figure out the point force representing the triangular distributed load is the height of that triangle. So how are we going to figure out the height of that triangle? That's right. It's going to be this total height minus this. So the 5,000s cancel out, and you're left with just positive 2,500x. Okay, so now the area of the triangle, that's just the base times the height over 2. So that's, the base is x. Let me write that in here. This length is x. So the area is x times 2,500x over 2. So in this case, that's 1,250x squared. And the area of the rectangle is this height, that sort of ugly thing, negative 2,500x plus 5,000 times x. So negative 2,500x squared plus 5,000x. And again, this, at first glance, this looks like it's going to be negative. But it's not. It's a magnitude. All right, so now we've represented both of those. So we broke up the trapezoid into 2 different distributed loads, a triangle and a rectangle. We found the point forces that represent each one of those. And now we're going to redraw the free body diagram with just those 2 point loads there. So here's the piece we're isolating. At the center, we have a downward force that's equal to, okay, that's just the area of the rectangle. So that's a downward force with a magnitude of negative 2,500 x squared plus 5,000. And then we have a downward force representing the triangular distributed load of 1250 x squared. And then we have the internal loads, T, V, M. And this distance is just 2x over 3, and this distance is x over 2.
Where's the triangle on the right?
The location of those point forces, because the triangle's facing the other way. You know, it's always 2/3 of the way from the point end to the wall end. So, so you're right. Okay, thank you. Okay, 1250x squared. Okay, so I was wrong about that distance. So the distance is actually x over 3 from here to there. All right, so Newton's second law says, okay, so watch the signs here because this gets a little confusing. This one isn't too bad. I mean, that looks positive. It's going down. So you can think of this magnitude as multiplied by the unit vector 0, -1. And you just get 0, -1250 x squared. But this one, if you're thinking of this as a negative number, which is easy to do because it has that leading negative, then you're going to mess up the sign on that vector. So the way to think about this is remember that that's a magnitude, and you're multiplying that magnitude by a unit vector 0, -1. And so the signs of those things switch, and you get 0, +2500 x squared minus 5,000. And then plus t negative v is equal to zeros. So in this problem, there's no internal tension. V is equal to 2500x squared minus 1250x squared minus 5,000. So you end up with positive 1250x squared minus 5,000. And then the moment equation.
Rectangle, you have area of -2,500 x squared.
Shoot. Okay. So this should be x. Okay, so go back up to, sorry about that. Go back up to the free body diagram. That should be x. There should be an x here in Newton's second law. And then v should be positive 1250x squared minus 5,000x. Okay. And then the moment equation, the 1250x squared has a moment arm of x over 3. And that would be a clockwise rotation, so negative x over 3 times 1250x squared. And then another clockwise rotation, so minus x over 2 times, okay, so now you have to think about the magnitude of this again. This number here is the magnitude. So you don't want to put in the one that you got in the shear force. This is x over 2 times the quantity negative 2,500 x squared plus 5,000 x. And then plus m minus vx is equal to 0. So you get, I think that is m is equal to vx plus 416.6 repeating times x cubed plus, one of these terms is going to be, so that leading term is going to be, we got two negatives and then move it to the other side. So this is minus 1250 x cubed and then plus 5,000 x squared. And so m is equal to, yes, but then I moved it to the other side of the equation. Okay, so m is equal to vx minus, that must be 833.3 repeating x cubed plus 5,000 x squared. What? The 5,000, I didn't multiply by half here, right? So that's 2,500 x squared. And down here, that's 2,500. Yeah, thank you. And now we have to multiply what we got for v by x and put that in there. So m is equal to, we have 1,250 x cubed minus 5,000 x squared minus 833.3 repeating x cubed plus 2,500 x squared, and combine the like terms. M is equal to negative, I guess for that leading term it would be, I think that's positive, positive 416.6 repeating, is that right? X cubed. And then minus 2,500 x squared. And problems like this, where there's a million places you can make algebra mistakes or whatever, those derivative relationships really help on these. Like when I made that mistake about not multiplying that 5,000 by 2, Muhammad, we would have found that when I took the derivative of m with respect to x, and it wouldn't have matched v. Okay, so let's do the checks. dm dx is equal to 1,250 x squared minus 5,000 x, so those match. And then the vdx is 2,500 x minus 5,000, and that is equal to our q, which is this. Any questions about that? Yes.
magnitude where?
Yes. So like just worrying about the signs and stuff. Okay. So first of all, I guess the main thing I want you to remember is just that the signs here can be tricky, so you need to be careful. And if you're being careful, like anytime you think you might be confused about the signs, you can check for yourself, because all of these equations are only valid in this case from x equals 0 to x equals 2. You know, so just plug x equals 0 or x equals 2 into there and see what the value, you know, something in between those, and see what the value of this is. So if you plug in if you plug in 0, you can see it's positive. If you plug in 1.99999, you can see it's positive minus something a little smaller. And so it has to be positive over that whole range. And once you know it's positive, then the issue sort of comes when, so if you're just looking at this and thinking it's negative, then you can get confused when you go to Newton's second law and think, okay, it's a downward force. This is already negative, which it's not, you know. But now you write this vector as 0, negative 2500x squared plus 5000x, and then your signs are off. So what you need to do is, now that you know that this function is positive over the whole range, just remember that that's a magnitude, and you're multiplying that magnitude by a unit vector in that direction, which is 0, negative 1. And that switches the sign of this in the y component. Does that make sense? Or yeah. Okay. Yeah, that can be really confusing. Yes? You mean just start with the whole thing? Yeah, so if I give you a problem where this just in 3 meters, yeah, the equations would be different, but the same idea would hold. Those things that have negative leading coefficients look like they might be negative, but they're really positive, and you have to treat them like magnitudes. But yeah, it would change, you know, the total area would be different and all that stuff. Yes?
You also had the weight force.
Yeah, so you can always, any of these shapes, you can break them up however you want and treat them as individual forces. So if you had this, and then you also had a rectangular distributed load representing the weight, you could treat it as 3 separate point forces, one for the triangle, one for that rectangle, one for the other rectangle. Or if you want to combine the 2 rectangles, since they act at the same point, you could do that too. And if you wanted, you know, you could, so now that we know this stuff, you could use the rules for calculating centroids to calculate where the centroid is at the trapezoid, and then the total point force would be at the centroid of the trapezoid with the sum of those two. But it's just extra work. It gives you the same answer, so you might as well just keep them separate. Any other questions about that? So those are the hardest problems that you'll have to do. And I won't make you do very many of them. And yeah, but you should at least see it. But like I said, for the most part, the practicality of it, unless you have things going from 2 different directions, yeah, just walk around the back of the problem, and then it's an easier problem, you know. Or also, you know, if you just did this problem from right to left, it would also be easier. I just recommend always going from left to right, because you get in these habits that sort of keep you from making dumb mistakes. I still make dumb mistakes, but yes. Yeah, I mean, you're drawing it from you're still going from what's now your left end, but it works exactly the same. I mean, really, that's what, so any problem, you could draw the mirror image of the problem and do it from left to right. And so if you had, so if your boss gives you this problem, you can always just sketch it as the mirror image. Solve that problem, and it's the exact same thing as doing your cuts starting at the right and moving to the left. Nope.
You have to account for all of them, right?
Yes, that's right. So yeah, I did this one. So like it starts out as like you have to calculate those external loads and do the trapezoid thing. Now everything's quick. You don't have to do the external loads. The thing's a triangle. It's way easier. Whether you cut from the left to the right, though, does change what x means. You know, like here x equals 0 is this, here x equals 0 is the other end. And so your functions are kind of flipped around, but they still, you know, give you the internal loads at each one of those individual locations along the beam. But they wouldn't look the same. The functions would look different. But if you compared like the two answers, what they say about the internal loads at the middle of the beam, they would agree. Any other questions? Okay, let's stop. What day is it? Tuesday? Okay, see you Thursday.